Great, so we can start now. Is everyone able to hear me?
Yep.
Great. Yeah, thanks a lot for having me. My name is Corey Lynch. I'm a researcher at Google Brain, and I'm going to be talking about some recent work from our group. So before I get started, I just want to say I'm quite happy to take any questions as they come. So anyone who's in the chat is feel free to ask a question at any time. And so before we go on for the rest of the talk, I want to start with this video to motivate the talk. And so this is a video from 2007. And this shows a PR1 robot from Stanford performing a number of very useful tasks in a home. So we have tidying pillows, stacking magazines, picking up blocks, putting them away in a bin. And to those who are not familiar with robotics, these tasks might seem almost trivial. So most humans, even kids, could do what we see here. But this is very much an open challenge for robotics and for artificial intelligence in general. So what actually makes what we see here so challenging? These are simple tasks, but what makes them challenging is that they demand intelligence and what we could call common sense about how to operate in unstructured environments. And so not just common sense, but also the coordination of things like raw perception and low-level control of a body. And so another reason we might call this an open challenge is that this robot isn't actually operating autonomously right now. It's being teleoperated by a human. And so while this might seem like kind of a problem, this came out in 2007, this is actually a great sign. This shows that we've actually had the hardware for a while now that is capable of performing lots of real world tasks. So this shows us that all the real bottleneck right now is learning software. We need to just figure out the learning software to get it to do these things. So let's take a look at some recent learning software for robots. On the robot learning side, there's been a lot of really impressive work recently using approaches from reinforcement learning, imitation learning, or combinations of both. And so, however, a lot of this typically involves learning a single task. So for example, on the top right here, you can see this robot has learned to flip this cube into a pan. And what's interesting about a lot of current robot learning is that it's typically learning a single task, and to get it to do the task on the top left, screw a cap onto a bottle, you would need to retrain the robot from scratch. So learn a completely new neural network. And so as we think about the first video, a natural question we can ask ourselves is, how do we actually scale up robot learning towards that setting? There's three important directions that people are thinking about right now. So first, how can we go from one robot, one task, which tends to be kind of the norm right now, to one robot, any task? We've seen that robots become excellent specialists. What we're wondering now is, how can we make them become more robot generalists? Second, how can we get robots to learn entirely from onboard perception, like RGB cameras? So this is important because these are the only sensors that robots are going to get to bring with them when they're deployed in, say, a home. And third, say we've trained a robot to execute a large number of skills. How can humans actually guide all of these skills or select these skills in a really flexible and intuitive way? And so this motivates new forms of conditioning, like natural language. So the central motivation for the rest of this talk is, is there a way that we can push up on all three of these at the same time? So before we go further, when we're thinking about going from one robot, one task to one robot, many tasks, it's very useful to ask ourselves, what do we mean by task? What is a task? So if we look at these three videos, we can see three instances of a robot opening a door. But if we look closely, we can see that there's actually a fair amount of variation in how it's doing it. It's grasping it from the top, it's nudging it from the left, or it's grabbing it from the bottom. And so if we think back to the first video of the kind of present robot learning, a lot of this would actually involve learning separate policies for each of these skills. And so if we consider things like this as well, is this close the door full or close the door partial? Both of these accomplish the same goal, but there's a lot of variation in how. And so the point of this is just to say that the real world has infinite kinds of these small variations in task. There's also, if you look at something like pick up the block and then close the door, where is the task boundary between these? What do you call the transitioning behavior in between? like, is this 3 tasks, 1 task, or 2 tasks? It's hard to say, really. And the point of this is all just to say, tasks aren't really discrete, and there's infinite variations around them because the real world isn't discrete. It's continuous. It's messy, and it can't really be described by a nice set of predefined tasks. And so robots that want to get out of the lab are going to have to contend with this fact at some point, we think. So we prefer to think instead of skills as living on sort of a continuum. And so you can imagine all of these different skills. There's infinite variation around each one, and there's not really a clear boundary between the individual discrete skills we might name. And so if we think about this sort of metaphor, we'd like agents to learn the full repertoire of general purpose skills in an environment, and the ones that we define by hand are really just the tip of that iceberg. So for background, before we get into the methods that we're going to present, let's go over 2 popular current ways to teach robot skills. So we have reinforcement learning and imitation learning. In reinforcement learning, we typically define a set of tasks that we care about. We define a reward for each of those tasks. And then a robot uses autonomous trial and error learning to maximize that reward. So what makes this hard to scale to the setting of one robot, many tasks? First, reward design is incredibly difficult, and it's often pretty task specific. And so this is something that we can't really imagine paying as a cost each time we move towards infinite tasks. Second, rewards are often heavily instrumented, especially in the real world. And so in the setup we see on the right, the robot gets some instrument that tells it whether or not it opened a door. And if we think back to the first video, robots in the home aren't going to get anything like this. So second, RL assumes good exploration, which is often very hard to guarantee in settings like manipulation and requires a lot of task-specific exploration strategies. And finally, reset mechanisms are something that is not always talked about, but is incredibly important in reinforcement learning research. RL needs to be reset to the initial state. And this can be incredibly human intensive and task specific. So for example, a few years ago, we were training a robot to pour beads into a cup. This is a failure case, and this needs to be reset every time. And in many cases, humans are the reset mechanism. So here's a picture of myself and Eric Jang, a colleague. And this is us at 2:30 in the morning, resetting the robot to the initial state of the scene. And so as you can see, this is just for one individual skill. If we'd like to go to many skills, we can't be there pouring beads back into the cup for every one of these. So let's talk about imitation learning. This is the kind of other broad approach that is very popular right now. The typical idea here is that you're also defining an upfront set of tasks. You're collecting human demonstrations for each task. And the idea here is just that sometimes it's much easier to just show a robot how to do something rather than to define a reward. And so here we're collecting a large data set of states and actions that are human supervised labels. And we're simply training a policy that maps from states to actions using supervised learning. So why is this hard to scale? The simple fact is that if we're going from one task to a ton of tasks, we're going to have to collect a large number of curated demonstrations for each of these tasks. So if we'd like to start in a new position, you now need to collect a whole new set of a new data set. So as we can see, this is quite expensive. So in summary, both conventional definitions of RL and IL are difficult to imagine to scaling to this in kind of the whole iceberg of skills, because both require defining tasks up front, and both require this large non-transferable human effort for each new task you arrive at. And so we have these per task costs like demonstrations, rewards, exploration, reset. And so this makes it hard to scale to single robot any task. And finally, even if you kind of did get there, there's these open questions that we'd like to address, like how do we actually just say what we want to a robot and have it do what we want? So with all this context in mind, the main questions that we're going to be guiding the rest of this talk are, instead of learning specialist policies for each new task, can we learn one general purpose policy? And so we're really looking for methods that can kind of attack the entire kind of iceberg, not just the tip of it. Second, let's say that we need some supervision to help overcome things like exploration. What is the most efficient way to transfer human knowledge to robots? So for example, what is the least amount of human input we can give on the left to get the most output that looks like the behaviors on the right. And then finally, is it possible to train a single neural network to perform language understanding, vision from raw onboard inputs, and low-level continuous control all at the same time? So as we think about the prior methods, something like doing one big network for perception, language, and control is something that's either really challenging typically for RL right now, or very expensive for labeled supervised learning. But this is actually a setting where large-scale self-supervised learning has had a lot of recent success. So if we look at a lot of recent success in NLP, we can see a common recipe, which is collect one big unstructured data set, something like all of Wikipedia, and then let's train a giant model with a simple objective. And the result is we can see very strong evidence of general purpose behavior that can be fine-tuned or conditioned to good task-specific behavior. So the question that we have is, can we do something that's similar, or has kind of a similar recipe set up for robotics? Yeah, and so with these questions in mind, I'd like to introduce the first work that we're talking about. And this work is called Learning Latent Plans from Play, or LFP, and this is something we presented at Coral in 2019. The first major ingredient to this approach is a big teleoperated human data set. So here on the left, you see a human taking control of the robot and playing with all of the objects in the scene in as many ways that they can think of. And so you can think of this as one long demonstration of how to do every single thing in the scene. And so there are a couple interesting things about this type of collection. One is that it bypasses a hard exploration problem. We mentioned earlier that like things like RL need to overcome really hard exploration problems and manipulation. What we're doing here is we're having humans cover the entire state space for the robot. And what humans bring to bear here is really interesting. They have tons of prior knowledge about the environment, even if they've never seen the environment before. If humans see a button, they know they can push it. If they see a drawer, they know they can open it. So they tend to do these things. And second, humans also get bored. So humans play with the door for a little bit, and they get bored. So they naturally transition to the block or to the drawer. And so in this way, this leads to a natural coverage of the entire state space because you're actually having humans do it. And so since we're in a simulator, we can actually quantify things like how well does play cover the state space as opposed to, say, random exploration or demonstrations. And we can see here on the top that play for the exact same amount of collection time, 1.5 hours, covers 4 times more space in this simulated environment that we have here than 18 tasks worth of labeled task demonstrations, and 14 times more space than random exploration, which is the kind of thing you might see at the beginning of reinforcement learning, for example. And we think this highlights how play, or kind of unstructured demonstrations, is a really efficient way to cover complicated state spaces. And so we can think of this as kind of covering not only the skills that we typically define for robots to learn, but also the things like all the transitions in between. And so another thing to point out is that practically using teleoperation to drive skill learning is not something that's new at all. It's been around in various forms for over 20 years now. We can see kind of like a couple example works from going back 20 years here. So what is different about this kind of collection? So the key idea is that free-form play is far less burdensome for humans to provide, which makes it, we think, makes it very scalable. And the reason for this is that there's no upfront task definition. Operators are free to do whatever they want. And so as we can see on the bottom, this is something that we're actually quite good at, is taking control of a robot, perhaps exploring the full scene and figuring out how everything works, because this is something that we've done naturally since we were very little. And a nice byproduct of this sort of free-form collection is that there's no task labeling or segmentation. And there's also no need to stage or reset the scene. So all of this means that we can be collecting this kind of data, like large amounts of human data, continuously and in large quantities. And since there's humans collecting, as we mentioned before, there's lots of rich natural demonstrations. This isn't by any means random. It's very directed. You can see examples of it picking up the block, opening or closing the door, sliding the pressing buttons. These are all things that you kind of get for free by having humans do it. And we think this sort of unstructured format better matches how unstructured the ultimate test setting is. And so in summary, we like this because we believe this is a very efficient way to transfer the most common sense kind of learning to robots. So we have this kind of collection. How do we actually learn any sort of meaningful control from this? So in this work, we're going to restrict our attention to pure imitation methods. And the most common imitation method is behavioral cloning. So in this setting, we have collected some demonstrations for a task, and then we're going to learn a mapping from state to action using supervised learning. So a very simple learning objective. For example, we could collect some state actions and then learn a policy pi that maps from inputs like onboard robot images from pixels to outputs like joint torques actually controlling the arm in the scene. Like as a reminder, we'd like to train not just a single task policy, but rather a single policy that's capable of executing many tasks. And so one kind of way you could modify simple behavioral cloning is instead conditioning on some sort of task ID. So we could say condition on door opening or condition on button pushing. But as we mentioned, this is actually like a little bit inflexible for the true setting that we care about, which is do kind of all of the behaviors in the scene. So not just the ones we can enumerate, but kind of anything you can think of. And so this is what really motivates goal reaching as a training objective. And so in goal reaching, we're going to define a general purpose policy as one that is capable of reaching any desired goal state in a scene from any initial state. And so the hope is if a policy knows the right actions that navigate between any two possible goal states, you should be able to give it any desired goal state at test time and have it do the right behavior. And so this is the formulation you see on the right here, and the one that we take on for the remainder of this work. And this is a kind of a modification of behavioral cloning, where the action prediction is conditioned not only on the current state, but on some provided goal state to reach. And so what's nice about this definition is that here tasks are defined in a continuous manner. When states are continuous, the tasks are continuous. And so this means we actually have the possibility here to represent infinite tasks. And so another nice thing about this is that you can think about a well-trained policy that knows how to use its body and objects in the scene to get between any two states as one that encodes a lot of common sense about the environment. And this is kind of our original objective. Like how do you go from closed door to open door? How do you go from messy desk to tidy desk? These are all things that require common sense. And so if the one on the left is one task, the formulation in the middle is multiple tasks. This is hopefully like a well-trained policy is in any task formulation. So how do we actually train this objective? We've defined an objective. How do we train it? If goal reaching is our training, where do we get the inputs to the supervised learning problem? The answer is we mine them from play automatically. So the key insight here is that any random window from play contains the exact information for how the agent got from some initial frame to some goal frame. And so here we see some different random window. This different random window contains a different initial state, a different goal state, and a different action trajectory. We see that the first one defines door opening, and the second one defines something like we might call push the red button. But notice that there's never a discrete task label. There's just the information. How did you get from this continuous state to that continuous state? This is a continuous task formulation. And so we want to highlight how data efficient a scheme like this is. So let's take 60 seconds let's take an hour of free-form continuous play data that a human collects. Since we can slide this smaller window over the full sequence, we can produce a large number of unique individual tasks for 1 hour. So in this case, 1 hour with like all 1 to 2 second windows sampled from 1 hour, you end up with 36,000 unique training examples that go into your training, and roughly 10 times the original hour that you put in. And so this just highlights for us at least how efficient something like relabeling on top of continuous collection works. And so how do we concretely learn control? This summarizes our training process. First, we're going to start with this long stream of teleoperated play, and we're going to log all of the onboard observations and actions. Next, we're going to define a neural network, pi theta, which maps from current onboard images and goal onboard images to the next action that accomplishes the goal. I'll discuss the implementation details in later slides. So next, we're going to sample all 1 to 2 second windows from the stream. We're observing at 30 hertz, so this is all 16 to 32 length sequences in the dataset. We're going to treat the last image in the sequence, in each sequence, as a reached goal image, and then hand the first image to state, the last image to SG or goal image, and supervise the network with a standard maximum likelihood supervised learning loss. We're going to call this kind of whole process learning from play, or LFP. So how does this actually work? At test time, we obtain a single task agnostic policy, and we're going to evaluate it on 18 test time only manipulation tasks. So here is an example of all of the tasks that we look at. We see things like close the drawer, close left, close right, grasp a flat object, grasp and lift from a drawer onto the table, put the object in the shelf, sweep it left and right, rotate it, press all the buttons. So we tried to come up with like 18 things in the scene that we could think of that a user might try to command. And so what's interesting is that when compared to 18 individual task-specific policies, this sort of self-supervised skill learning method is actually capable of exceeding 18 of these individual policies. And so after self-supervising on 7 hours of play data, our goal condition policy is able to exceed the performance of 18 individual trained on the same amount of data. So here's examples of some test time rollouts. Here is the goal provided to the network, and here's what happens. So this is sort of a door opening task. We give it an image of a door that we'd like opened, and it does the right thing. Same thing here. We have kind of a goal presented as sweep this object into a drawer, and you see the rollout on the right. Same thing for kind of press a button, pick an object up, put it on the table. And so what another interesting that we noticed is that training on top of play, on unstructured play, actually makes policies at test time much more robust. And so this is actually a huge problem in imitation learning, is the idea that you can get knocked off of some initial trajectory and then encounter compounding error. And so we test this by adding noise at test time to train policies. And we see that policies that are trained on more conventional narrow task demonstrations degrade pretty substantially. So they drop from around 70 to 23%. Whereas models that are trained on relabeled play, despite having no kind of task definitions, are degraded far less by adding noise at test time. And so this actually, this helps in a pretty practical way solve a pretty common problem in imitation learning methods, is just training on less structured data. So as a summary, we want to collect the summary of this method. We're going to collect some large unstructured unlabeled play data set. We're going to perform relabeled GCBC on it, or goal condition behavioral cloning. And then at test time, we're going to condition on some user desired image to define some task. So why do we like this method? It involves a simple collection. There's no upfront task definition. There's no task labels. There's no exploration because humans are providing the exploration for the robot. There's no reward design because these are imitation methods. And second, it's a simple learning objective. So it's easy. You can easily scale something like this to kind of arbitrarily large neural networks, including learning from raw perception. And you can do things like train on many tasks at once at training time without encountering any sort of instability. But kind of not everything is kind of perfect here. When we think about the kind of original three directions that we're trying to push on, this may make some progress towards going from single robot, single task to single robot, many tasks. It scales comfortably to learning from onboard images. But what about conditioning? So if we look back at how this model is trained, the only way that a human being could condition or guide the behavior at test time is providing a goal image to the robot. And so if we look back at the guiding motivation, this would be kind of difficult. You would need one goal image for every single task in the room. You would need one for the arranged pillows. You'd need one for the blocks, one for the magazines. And as we can see, this could start to get quite impractical for humans to actually provide a test time. And so this becomes the main consideration of the next work I'm going to present. And this is the question of scalable human conditioning. How do we actually control robot behavior in a scalable and flexible manner? And so the question we asked ourselves is, why not free-form natural language? This seems to be the most flexible and the most scalable way for humans to control robot behavior. So this is the subject of the next work, and this is called grounding language in play, or we call this Lang LFP for short. And this is some work that is going to be presented this year at RSS 2021. So the kind of the two main questions that we have going into this work are the first one, which is kind of obvious: how do we control robots with free-form text? But the second one, which is not as obvious, is we just kind of motivated things like using self-supervised learning over unlabeled imitation data sets. How can we keep all the benefits of relabeled learning, which is incredibly efficient, while also trying to learn language condition control, which seems like it kind of needs to be supervised in some way? So how do we marry unsupervised learning here with supervised learning in an efficient manner? So our approach is it's actually pretty simple. We're going to first pair play that we're collecting with human language. And so the idea here is that this is kind of the familiar setup that we just saw, which is one big unstructured human play data set that gets relabeled into many small windows and ends up in a data set of demonstrations paired with goal images that they're solving for. What we're going to do is take a small number of these windows from this original data set, so 1%, or less than 1% rather, and we're going to hand them to a crowd compute, or like an Amazon Mechanical Turk, some service like this, and we're going to present people who are like crowd compute raters 1 to 2 second windows, where they watch the video, they look at the first frame, the final frame in the video, and then they answer the question: what instruction would you have given the robot to go from start to finish? And so we don't put any limits on grammar or vocab here. We want the collected instructions to be as natural as possible. And so much like we collect hindsight reached goal images, we can consider this a hindsight reached instruction. This is an instruction for which the video is optimal. And so much in the same way that we obtain kind of demonstrations with the goal image that solves for it, we're going to obtain a much smaller data set of demonstrations paired with instructions that match the demonstration. And we can use both of these as training data. And so another thing to point out about this, here's some like actual examples of 1 to 2 second windows that we present to raters, and some of the instructions that we got back from them. So this is real training data. So you see things like slowly move the door all the way to the left, move your hand towards the drawer handle, roll the block to the left and then grasp the block, roll the block to the left, lift the object up to the left, press and release the red button. And so you can see here that because this whole process sits on top of relabeled play, or small windows drawn from play, it gets all of the kind of diversity that you would expect from grabbing 1 to 2 second windows from some passive collection of doing anything in the scene. So now we have two data sets, one with image goals, the other with language goals. We'd like to learn one big unified policy that can solve for either image or language goals. So to do this, we're going to train a single policy on both data sets at once, where image goals and language goals are mapped to the same latent space. So to be able to do this, we're going to have to introduce a new form of imitation learning that is different than the objectives that we presented in the prior slides. And we're going to call this multi-context imitation learning. And so much in the same way that multitask imitation learning might train a policy to generalize to multiple tasks, we're going to try to train a single policy that generalizes to multiple conditioning contexts. So what does that mean? Here we're going to start off with the multiple imitation data sets, each one with a different kind of task description. So on the left, you might have demonstrations paired with goal images that were reached. On the right, you might have state actions paired with natural language that was reached. And this is actually a setup that we think is increasingly common in imitation learning, that we have not just one, but many data sets, each with a different task description and each with a different cost of collection. So the one on the left is actually much easier to collect. It's all relabeled. The one on the right required some human annotation. And so instead of training one goal condition policy for each of these data sets, we're instead going to train a single latent goal condition policy over all data sets simultaneously. And here we're going to learn to map each of these task description types into the same latent goal space. So to do this, we're going to have to define let's say one kind of encoder for each of these contexts that are both projecting to the same latent goal space. And so intuitively, training is simple. At each step, you're going to grab a batch from each data set. You're going to encode all of the context into this common latent goal space, infer common latent codes for all of these examples. And then you're going to take a gradient step on a maximum likelihood imitation objective. So still maximum likelihood imitation. It's just that we're first projecting goals to a common space. And so being context agnostic in this way enables a very highly efficient training scheme that we couldn't do if we didn't map both to the same space. And that's learn the majority of control from the cheapest data source that you have. And so this formulation is exactly what allows us not to have to collect labels for every single window in the data set, but rather collect language annotation for only less than 1%. And so this is critical because it allows us to reduce this cost of language collection to something that can actually be practically applied. Like we didn't have to hand 10 million windows to crowd compute. We could get away with a few thousand. And another thing that's nice about this formulation is that it's quite flexible. So you could imagine adding another data set that has, let's say, some tasks that you care about conditioned with task IDs. And you could just continue kind of projecting these new context types to the same latent space. You could imagine kind of pairing this with demonstrations and human video goals to reach. We think that this is a fairly flexible way to learn kind of one robot, any context.
Can I ask
So,
a question?
Yeah, absolutely.
So are the encoders learned in a separate process, or is it all one big process?
That's a great question and something I forgot to mention. Yeah, so an important thing to mention is that all of this is trained end to end as one neural network.
That's quite incredible.
So to make this concrete and put this into context, let's compare this to previous forms of imitation learning. And so left to right, we have no conditioning, so single task ID conditioned, or goal image conditioned. This was like the LFP or previous version. And so now we're going to call this MCIL, or multi-context imitation learning, where we're going to define this very similar idea. You're going to define a neural network mapping from a kind of onboard state and some goal to some action. But you're first going to define these separate image encoder and language encoder with separate weights. And we're going to map the kind of image goal and the language goal into Z first, then map state and Z to action, imitation loss, and then imitation loss gets back propagated through the entire stack. And so if this is on the top left is single task, middle is multitask, right is goal image, this is going to be goal image and natural language. And so that's what we see here. This is kind of the second kind of systems level overview of what we're doing is train one big policy on images, language, and then of course from raw perception at the lowest level. And so finally, at test time, we only use text conditioning here. So to kind of sum up the whole process, we're going to first pair play unstructured play windows from it with language. We're going to train a single agent to follow image or language goals, and then at test time, we're going to follow multiple text instructions in a row. So, for example, things like kind of open the door, now pick up the block, now push the red button. And it's important to note that these are all going to be, because these are all 1 to 2 second windows grabbed from play, each of the instructions kind of has to be a description of a short horizon goal. So you're not going to be able to say something like clean up the whole room, but you might be able to say something like pick up the block, now put it on the left side of the desk, now close the drawer. So here are some implementation details. We moved implementation details to kind of later here because this sort of subsumes the original details. We're using very similar architectures in both. Again, we're learning here perception, language, and control kind of all as one neural network. And so I'm going to break down the different modules, but these are all trained kind of end-to-end. And so first we have our observations consist of a 200 by 200 RGB image that comes from the kind of egocentric view of the robot. And it also has the robot has access to its own 8-dimensional proprioceptive information. So this is the Cartesian position of the end effector and the Euler angles describing its rotation, as well as 2 angles describing whether or not the grip, how the angle of the gripper. And so what we're going to do is feed the image through a deep neural network with a soft spatial attention over the convolutional feature map that gets reduced and then passed through an MLP concatenated with the proprioception. And we're going to call this whole module kind of a perceptual embedding. So you end up with this 64 plus 8, 72 perceptual embedding that gets reused kind of throughout the rest of the stack. On the language side, we're going to map a kind of a free-form sentence of any length through a subword tokenizer. And so what this does is, let's say it takes the word like opening and breaks it down to open and ing. And this allows you to kind of share statistical strength among the word opening and the word open. And this tends to be like a common way of tokenizing raw text. We're going to map each of these subwords into an embedding and grab the embedding for each one of these sentences, concatenate it. We experimented with different ways of reducing this into kind of a sentence summary. Average pooling works surprisingly well in this setting, but we also what worked equally well was like running an RNN over this embedding sequence. Then we're going to hand this through a pretty wide MLP that projects to some latent goal, sort of to the shared latent goal that we're talking about. And then finally, this is kind of what control looks like. Reminder that we have these 2 paths, one that is conditioned on goal images, the other one that's conditioned on language, but they share the majority of their networks. And so let's talk about the goal image path. The goal image path looks like original LMP or LFP. You're going to hand the current image and the goal image both through perception stacks. Both are shared. On the goal image side, you're going to map it further through an MLP that projects to the shared embedding space, the shared kind of visual lingual goal space. You're going to hand the visual state and this kind of shared Z to a recurrent neural network, and the recurrent neural network is going to output an action. On the language path, you're going to do something very similar. You're going to use this shared perception stack to process the current image into some visual embedding. You're then going to use the language embedder that we just described to map open the door to like some point in latent goal space. And we're going to pass this through a recurrent neural network. And having memory in the control is actually quite important when you're doing things like rotate the object left, because you actually need some memory of kind of where the object started to be able to correctly do this in closed loop. So let's talk about experiments now. The experiments were conducted in the same desktop environment we saw here. We collected 7 hours of play and 10,000 language annotations. And just as a reminder, that's a small fraction of the total number of windows. And as mentioned before, the robot receives onboard pixel observations at 30 Hertz. And the robot can be conditioned with either goal images or text. We're going to show just the text conditioning now. And we evaluated on the same 18 different manipulation tasks, just that now we've paired each of these 18 tasks with a fair amount of natural language instructions to be able to do the evaluation. In the same way that we collect kind of training data, handing short videos to raters and asking them to provide some information. And so we're going to look at these experiments that are not just single kind of one-off single task experiments, but really trying to get more towards the setting that we care about, which is doing a large number of tasks in a row. And here you see rollouts on the right. This is a long horizon benchmark. And so it ranges from, on the x-axis, from 1 instructions in a row to 4 instructions in a row, where each instruction is some natural language sentence provided to the robot. And so you can see that as you go from 1 instruction to 4 instructions, the total number of possible kind of unique tasks really blows up. You go from 18 to over 925 tasks that you're evaluating a single policy on. And the point is to test, can we go from 1 agent, 1 task to 1 agent, like very large number of tasks, kind of all the tasks you can think of in the scene. And so this is showing one of these evaluations. And so in the kind of now screen, you can see what's being typed in to the robot, push the block into the drawer, push the drawer all the way in. And in the gray, you can see what's being queued up next as a natural language input for the robot. And so pull the drawer handle all the way, put the block in the drawer, push the drawer in, move the door all the way to the right. And so we can also try to test, like, how far can we actually push this? Can we do like 15 instructions in a row, which is a pretty long horizon for kind of most kind of current imitation learning and reinforcement learning methods. And we can see that if you watch the video, that we can kind of get the robot to do 15 kind of arbitrary ordering instructions in a row. So pull the drawer all the way, then drag the block into the drawer, then close the drawer, then push the drawer all the way to the right, and so on. And we're going to show this at 2x speed. And since I'm kind of running out of time, I'm going to keep going. So one thing to notice here is that if we look at kind of rollouts, especially over long horizons, training on unstructured data is actually incredibly important. And so knowing how to transition well is itself a useful task. And this is covered in relabeled imitation, but it's not necessarily covered during a narrow collection of expert tasks. And so you can see this like really starkly on the right. The play train models are able to kind of take all of the language instructions and perform them all in a row, whereas the conventional demo train ones tend to get stuck in these loops where you get slightly off of your training distribution and you can't recover. So unstructured data is a really nice way to mitigate this common failure. Another really interesting aspect that we notice is that play scales with model capacity. And so just scaling up model capacity only in the play train models leads to better performance. And so we think of this as large capacity is absorbing all of this diversity well, but overfits less to diverse data. And so I'll skip forward to the concept of knowledge transfer. We mentioned earlier training on this idea of kind of collecting some training instructions, feeding them to a policy. What if we instead, before feeding them to a policy, pass them through the embedding space of a large pre-trained language model? So what's interesting about this is that it actually improves the manipulation performance, but it allows you to do something really interesting at test time, and that's follow synonym instructions kind of for free. So here we can see the instructions that it's been trained to follow, like open the door, and some new test time instruction, like slide the panel all the way to the right. And we see here that the large pre-trained language model is responsible for mapping these new instructions to ones that it's been trained to follow. And so like another interesting thing that you can do is just choose a multilingual pre-training. And that means you can start to follow instructions in new languages for free without ever having robot demonstrations. So this is exactly what we see on the right. We see this is my co-author Pierre typing French to the robot. And the robot is following instructions in French, even though it was only ever trained in English. And so this robot now knows much more French than I do. If you gave me the same instructions, I would have no idea what to do. But just kind of through this clever choice of pre-trained language model and pre-trained kind of combination of large language model and robot, it's able to follow these kind of fully zero-shot instructions or fully out of training distribution instructions in zero-shot. So this, as you can see, we constructed these benchmarks where you have 15,000 kind of out of distribution English synonyms and 240,000 of these 16 language tasks. And we can see that the model actually holds up quite well in this pretty like extreme setting. So here are some important takeaways from these experiments. One, human teleoperated play, we think, is a very scalable way to get an unstructured data set of robot experience. You can train one big model that does perception, language, and control on top of this. And you can do it with a very simple objective that is 99% self-supervised, 1% language labeled. Second, we showed that transfer learning from large pre-trained language models is an effective way to improve robot manipulation performance. And it also allows us to follow zero-shot synonyms. That's all I have for today, and thank you so much, and I'm happy to answer some questions.